Okay, welcome to part two of wave characteristics and the nature of waves. Um, Mechanical waves can move in one of two ways, and it has to deal with the direction of the vibration of the particles compared to the direction of the motion of the energy. If the particles, and here's a position where the hand is going up and down, move perpendicular or 90 degrees to the energy of the wave, and the wave itself is moving across toward the right, then we call that a transverse wave. It sets up the classic wave shape that you think of with a sine wave or a cosine wave or curve. If the particles, this time the hand is pushing in and out on the spring, if the particles move parallel to the energy, so the energy is going to move this way again. If they move parallel to each other, then we call it a longitudinal wave. Sound's a good example of a longitudinal wave. Making waves on a string or a spring is a good example of a transverse wave, bouncing it up and down. So diagram A shows a transverse wave, and diagram B shows a longitudinal wave. In the longitudinal wave, there'll be sections of compressed material. Those are called compressions. And then sections where the material is spread out, those are called rarefactions. Those do not occur in the transverse type wave. Again, in the picture, if you look at comparing the direction of the medium for the longitudinal wave here, again, this is longitudinal along the spring, in this case, longitudinal. The energy is moving back and forth, bouncing off that wall and coming back. The hand is also moving in and out to the right and left direction. So those two are parallel to each other, so that's longitudinal. Here, the hand is moving up and down, and the energy is going to move out and it's going to bounce back. So that's transverse. In terms of wave characteristics, here again is another drawing with the wave characteristics. The wavelength, the symbol for the wavelength is lambda, Greek letter lambda. Instead of using L for length, which make it confusing with other L's we've used, they went with the Greek letter lambda. Still an L. Trough, again, low point. Crest or peak is a high point. Wavelength can be between here and here, or it can be between here and here, or it could be between here and here. Any two like points. Now this is not a wavelength, and that's because these 2 points are what we call out of phase. The next motion on this particular particle here would be to go down, but this particle would be going up, so they'd be in opposite directions. To have a full wavelength, it has to be between 2 points that are not only at the same distance from equilibrium, and this again is your equilibrium position, but they also have to be moving in phase, moving in the same direction. Okay, so in my picture here, 12, a wave is introduced into a medium, and we have a snapshot of it. It wants our crest. Crests are any top point, so B and E are crest. It wants our troughs. Those are low points, so D and G. Places where it's neither would be anything that's not one of those two. A and C and F and H and I and J. Okay, any of the other letters. So crest, top point of the wave, highest point, trough, lowest point. Anything in between doesn't really have a specific name, although something like C is at the equilibrium position. That's an important position with waves. Okay, here you're looking for the wavelength. The wavelength is given by letter A. Wavelength is the same distance between any two like points, so here it's crest to crest. The amplitude is D. Okay, be careful with the amplitude. It's not the entire height from the highest point to the lowest point. It is the distance between the high or low point and equilibrium. So here's between the trough and equilibrium. This would also be an amplitude. This would also be an amplitude. This would also be an amplitude. In a typical wave, those should all be the same. Here is a sine curve. Makes a good example of a transverse wave. We can measure the distances, the amplitudes, and the wavelengths. We just have to find any 2 points that will work on our ruler. So here's a low point, which looks to be at about 2.8. And here is another low point, which looks to be also, it looks to be about 6.8. So the difference between those two would be approximately 4 centimeters. And then in terms of the amplitude, here is 0. 0 is at about 0.8, and here's the peak, which is at about 1.7. So 17 minus 8 is 9, so that would be 0.9 centimeters. Again, depending on how close you're measuring that, it might be 1 centimeter. Just want to measure it. You can measure it in terms of both distances, and you can also measure it in terms of time. All right, now a very important concept in waves is they have how often they occur. So the number of cycles per unit time is called the frequency. We dealt with frequency when we talked about pendulum. A pendulum has a certain frequency that it goes back and forth, how many times it goes back and forth in a period of time. The typical unit for frequency is the hertz, Hz, and a hertz is equal to 1 cycle of the wave in 1 second of time. So example for 16, using the hertz, the frequency of rotation of a second-hand clock is, well, it takes 60 seconds to go around once. So the frequency of the rotation of the second-hand clock is, for every second, it would go around 1 click, which would be 1/60th of the full rotation. So the frequency of the second hand would be 1/60th hertz. 1 cycle for every 60 seconds of time. 1 complete cycle around for every 60 seconds of time. Pendulum, talked about pendulum earlier. If it makes 20 vibrations or 20 periods, now for a pendulum, that would be over and back. 40 of those in 20 seconds. The period would be 40 cycles per 20 seconds, which is equal to 2 hertz. 2 cycles every second of time. Now, another term that we're going to need to use is period, and the frequency is equal to the inverse of the period. So if you have a frequency of 2 hertz, 2 cycles every second, then that means it would take 1/2 of a second to make 1 cycle. So that's an important relationship between frequency and period. Okay, in this part we're looking at Olive, and Olive is swinging back and forth 1 time every 5 seconds. Now that statement could provide us with the period, 5 seconds, but we could also calculate the frequency because we have 1 cycle every 5 seconds. So as long as you know one of those, you always know the other. So if you know the period, you know the frequency. If you know the frequency, you know the period. They are simply the inverse of each other. The frequency of Olive's periodic motion is 1 cycle every 5 seconds. 1 divided by 5 is 0.2, and that would be cycles per second, which would be hertz. So a period of 5 seconds always corresponds to a frequency of 1/5 of a hertz, or 0.2 hertz. They're always the inverse of each other. So if we're looking at 21 here, the period of a 261 hertz sound wave is the inverse of the frequency. And again, 261 hertz would be the frequency. So if we take 1 over 261 hertz, we'll get 0.004 seconds. So that makes the period, the time it takes to happen once, a very short period of 0.004 seconds. So you'll find with a lot of waves, as the frequency goes up, frequency increases, the period will have to decrease. And if you do something more often, increase the frequency, then the amount of time you're going to be able to do that thing is going to have to decrease. So they're always inverse of each other. If one increases, the other always decreases. Okay, that finishes this round of waves. We'll move on to the wave equation next.